Hello, welcome everybody, and welcome to this NF Core training where we're going to go over a whole bunch of Nextflow material. This is the second of our trainings that we're doing currently, and each one is at a different time zone. So this is the EMEA one. This is the first session of the EMEA one. I'd like to point you to the materials here that we've got a little bit of a schedule and some information about all of the courses here. If you go to the NF Core website, that's NF-Core. You can find the information at the very top. If you see events, you'll see information. And if you're watching this YouTube link, obviously you've found the right location for the video. We have a few other materials that are available for us to use over these sessions now, including some chat, as well as some other material which will be made available. So if you can go to that website, you should be able to find most of the key information that we have there. So starting off today, you can see that we are in the EMEA session here, and this is session number 1. And you find most of the information will be able in the YouTube. If you want to come back to this in the future as well, you can always come back and find these which are recorded, and then they'll go up live some minutes after as well. So you can find that information there. So today we're going to start off with a little bit of an introduction on Nextflow, just 25 minutes or so, a little bit of background and sort of welcome and intro. Then we'll go into our first script section where we're just going to look at a very basic Nextflow pipeline, which is just made up of a couple of different processes. We're going to jump into a break, and then after the break, come back and we're going to be looking at a very simple RNA-Seq pipeline, as well as looking at how we can use containers and within Nextflow as well. The next sessions for the next couple of days coming up, we've got starting off with a lot of the kind of basic syntax of Nextflow, so understanding the channels, the processes, and the operators, followed by some work on modularization. So this is looking at some of the new features with DSL2, as well as some of the deployment work. And finally, then there's going to be a section on the community, on NF Core, some of the modules work, as well as Nextflow Tower, and something that we'll see on the final day as well. It's going to be spread across several different instructors as well. So hopefully you get a kind of variety of styles there. And it's the first time of us doing this format, but hopefully it works out well. If you've got any feedback as well, always welcome, and particularly on the NF Core Slack channels that we have there. So in terms of that chat here, if you've got any questions, you'll notice that there's these 3 Slack channels inside the NF Core Slack. So if you're not part of that Slack, you can join here with this link here. And inside of those, you'll find the three different channels which are specific for the training events. We have 4 or 5 people online at the moment who will be able to help you with questions, answer that. Obviously, with so many people on the video at once, it's a little bit difficult to answer all those things live as I'm going through it, but I'll try and keep an eye for any kind of questions that maybe are not specifically covered. Final thing is just on the materials. You don't need anything other than a browser and a GitHub account to run this. We're going to be doing everything in a Git pod environment. I'll show you how that works later, but essentially it's typically one click to access that. It pulls down the container, which has got Nextflow installed. It's got all our data, it's got all our scripts, and you can come back to that in the future as well. So don't worry about sort of having to this. I'll also show you how you can install Nextflow locally, but we'd recommend the Git pod environment for running that for starting off. So with that, I'm going to just jump over to some slides now, and we can get off and just kick off on the main part of the training itself. Okay, so just a little bit of background on how this comes about and sort of the problem that we're trying to solve. If you think about what we're trying to do, typically with these workflows, if you have any kind of experience in this, you'll know that it can be particularly difficult to essentially write these things. And this is really the problem that Nextflow is trying to solve. This concept that you have multiple different steps, different pieces of software that you're trying to link together. You typically have some input data that you're trying to analyze, and you're trying to get some answer out of that, some result. And in between is really where all the sort of messy details lie. The fact that a lot of our software is, maybe it's a script you've taken from someone in your lab, maybe it's something you've downloaded from GitHub, a bioconda environment, etc. And you have to pull all of that together into something which can essentially run, and not only just run, but run in a distributed manner. Run in a way where we're going to submit that across a cluster or into a cloud. And a lot of this compute that we have is obviously very large for doing that kind of analysis. It's also got this this concept that we want to be able to share that work. Maybe we want to take our pipeline, make it reproducible. We want to run it in different environments. And all of that presents lots of challenges to this kind of analysis. So here's an example of an ancient DNA analysis pipeline. And this is very fitting. If you would have seen the news from earlier this morning, you would have seen that there was the Nobel Prize for Medicine was awarded today for essentially ancient DNA analysis. So the timing of this is quite timely for this. And I'm not sure of the exact relationship between the software used here and the Nobel Prize, but I'm sure someone from the NF Core team who wrote this pipeline will let us know as well later on. Okay, so let's start summarizing the problem. We all have larger and large data sets that we're trying to analyze, typically sequencing data, but imaging data, or any of those kind of large data sets that we're trying to essentially run through and get some answers to. We've got this concept of embarrassing parallelization, the idea that we can take our data and it essentially runs through our pipeline in parallel. It means that we run through a particular process, a particular step for as many times that I have samples, or maybe I split my chromosomes up into regions and I run through each of those regions through the pipeline, and essentially in a parallelized way. This means that you can end up with tens of thousands of jobs, and each one of those jobs is typically having to be run on some sort of distributed infrastructure itself. We've also got a whole bunch of different tools that we're going to be using. These pipelines are made up of, as I mentioned before, just a whole variety of software, which maybe has differing sort of qualities in terms of the way that it was written, different programming languages, different environments, etc. And all of this creates this relatively difficult dependency tree. It ends up in situations where some pieces of the software maybe are incompatible with each other, or we have to maintain all of that. And I guess like the sort of coming at this from a few years ago, the main way, because the way that you'd come to do that would really be to install all those pieces of software individually. And this is the case that we sort of started at earlier on. Now, kind of looking forward, and what's the kind of goals of much of this, and what does this kind of enable with regards to Nextflow? Well, I'm sure you've all heard of fair data and this kind of concept that we can make the data findable, accessible, interoperable, reusable. We kind of like to extend that with Nextflow and take it a little bit further, not just from the data, but the data analysis itself. So in this case, making the data analysis findable, maybe available through GitHub or accessible in a similar way. Likewise, we like to think things are interoperable, that you can run the analysis on any cloud that's available. Reusable is obviously very tightly tied to the concept of reproducibility, and we see that with the use of containers and how we can run those things in a completely reproducible way. The idea that the data itself could be equitable, free of bias, scalable, be able to take from a laptop to a supercomputer, all the way up, as well as being tested. The idea we're going to use modern software engineering practices to be able to isolate pieces of our code, run them in isolation with small test data sets, etc., really using a test-driven approach to the development of the pipelines, just like we would other pieces of software as well. So, as I mentioned before, how was this sold before? How were we doing things, say, before things like Nextflow came around? Well, here's an example of a parasite genome annotation pipeline. This actually came out of the Sanger Institute some years ago, and it was really one of the first big pipelines that I was aware of that was written in Nextflow, and it gave us this glimpse into what people were essentially doing prior. Here you can see that each one of those circles is a process. It's a different tool which is being used. And you can see there's really a multitude of different tools that are a part of that pipeline. Each one of them had to be painstakingly installed on the machine that you wish to run the analysis on. Obviously, it presented a big challenge and was sort of a lot of time which was spent. That essentially got placed into a Nextflow pipeline, and then sort of show you the results of that in a moment. What was also kind of apparent at the time and related to this was just how hard it was to reproduce a pipeline, how hard it is to reproduce even an academic analysis. And this was a paper which looked at that and described that it said around 280 hours or nearly 2 months to, even when you've got the results, even when you've got the methods, all of the software, etc., just trying to go through it and get the same results was very kind of difficult. But the problem is slightly even worse than that, because even when you have all the site-right software versions, all the exact commands that we used, in that case, it's still not really enough to be able to reproduce a result. And this is what we showed early on in one of the Nextflow papers in Nature Biotech, was that even when you took a particular pipeline, like the pipeline I showed you before, but even some much more simple pipelines, that the results were different depending on the different machines that you use. So, for example, if I ran an analysis on a Mac, or if I ran the same thing with the same versions, etc., on a Linux, I got different results. And this is what we showed here, both in terms of gene annotation, so like the start signs or the start locations of genes, as well as, in this case down below, the actual genes which were called differentially expressed and using Callisto and the R package sleuth, we ended up being different depending on those things. And this was just two examples of pipelines we kind of picked up. And we sort of realized that this is obviously a big problem with regards to reproducibility in itself, and something obviously that containers have gone on to be very helpful for us, and just the importance of being able to reproduce those things. So that's kind of one sort of small angle on the sort of the idea on some of the topics that sort of Nextflow was involved in early on. Sort of stepping back a little bit about how does it work in practice? Well, with Nextflow, we can write code in any language. We've got this kind of concept of a language. It's like a script that we write. From there, we can take code. Maybe you've got some R, maybe you've got some Python, maybe you've got some command line tools, etc. And you take each of those and you wrap them in a process block. And it's those process blocks that get linked together with this data flow programming languages. This is where the data flow part comes in. You define the containers with that, essentially the dependencies, and wrap all of that into a Git repository. And that's what becomes a Nextflow pipeline or a Nextflow workflow in itself. Nextflow, as well as being a language, is also a runtime. So it's also the executor of the pipeline itself. And you have a bunch of different ways to run a Nextflow pipeline. You can run it locally on your machine. You could submit it to a Slurm cluster. You could submit it to the cloud. In each one of those situations, the Nextflow pipeline itself remains the same. So essentially, the underlying code of the workflow is identical. And where you submit the pipeline is really just dependent on some configuration. And it's that distinction, is that kind of difference between the definition of the workflow from where the pipeline runs, essentially, which has allowed the communities like NF Core and people to come together from all over the world, work on the same code base, and really kind of grow the community aspect of it from there as well. So diving a little bit deeper about some particular aspects of Nextflow that is, say, maybe different from some other aspects. It's a custom DSL. So this means it's a domain-specific language. So it's a language specifically written for writing workflows. And the idea here is it makes it very easy to quickly develop your pipelines. All of the key pieces which are required are there. So defining work processes, for example, linking those processes together, really kind of the core pieces that you would expect from a pipeline sort of language. But when you're in situations where there's something that's not available in Nextflow, maybe something outside the box, then you've got this ability to access this underlying programming language. In the case of Nextflow, that's Groovy. And the Groovy is essentially the underlying programming language that Nextflow is written in. And it's not really essential to know really any Groovy to write an Nextflow pipeline, but you'll see there's a reference section later on. It can be useful in some use cases where you're trying to something which is not possible in Nextflow itself. We have this concept of easy parallelization, and in this sense is a sense where the flow comes from on Nextflow, so it's a data flow model. In this case, you can think of like the data itself being in part of channels, and that is essentially driving the execution forward. It's this reactive in the sense that the processes themselves are reacting to the data. As the data comes through, they react to it and essentially execute it. This is different from obviously the pull model, which you'll see in something like make-like approaches as well. We also have a self-contained approach where every single Nextflow task lives in its own working directory. And every task is almost like independent of the other tasks. This means that it can be easily either wrapped into a container or submitted to a distributed infrastructure system like AWS Batch, for example. And in all those cases, this kind of idea of isolating the individual task, treating it like a unit of compute, can be very helpful as well for things like resumption of pipelines as well. And finally, I've got this idea of separating out the workflow definition from the execution layer, like I sort of mentioned a little bit earlier on as well. Okay, what does it look like? So I'm actually going to show you now a very quick example of DSL1, and that's the only time we're going to see this. And DSL1 was the original syntax of Nextflow. Under the hood, everything is exactly the same, but there's just a slight difference. So if you see this is slightly different from the thing, the point of this is that it shows you very clearly the linking between the processes, which I'll show you in a moment. So imagine that I have this task, maybe something you write in the command line or something that you have in a script. This is just BWA mem, and it's going to read essentially aligning the sample against this reference here. And then I'm piping it to SAMtools. To run this in Nextflow, you can simply take the original task itself. I'm going to wrap it in what's called a process block. And this is like the unit of compute. This is essentially like the definition of the process. You can see I've got the inputs, which in this case is the reference. I've got the sample, and then I've got defining the output, which is the sample.bam. And all of that is really wrapped in the script section here. And the script section remains exactly the same as I had before. Now, this is kind of simple enough. You can kind of see it. You'll notice that maybe these channels is a little bit different from something you've seen before, but really it should be relatively readable. So the way you can read this is that for each of these tasks of the aligned sample, the task will start. We'll have a reference sample and a reference and a sample. The script section will run, and then it will create a file called sample.bam. And this sample.bam will go into this output channel, this BAM channel here. What happens if I want to use this downstream? What if I want to take this, take the output of this process and then use that? Well, this is where the channels come in. And if I was to simply define a downstream task of this, so imagine that I had the output here, which I wish to use downstream, I could create a new process there, which in this case would be the BAM channel, which is this the input now. So the output of the previous task becomes the input of the next task here. And you see that kind of implicit linking of those two things provides the kind of parallelization going forward. So the way that you can think about this is both of those processes are kind of alive. When the first process sort of reaches and has its inputs, which are essentially reaching it, it'll fire off the execution of the first task. And then when the task is complete, it's going to place that BAM file into the output channel, which is essentially going to drive the execution of the index sample, which is essentially waiting there for that process to go. We're going to go see quite a few examples of this in practice as well. The evolution of Nextflow has sort of resulted in the slight syntax change now, where we define the processes exactly the same, except we just leave out this definition of the channels here. And the channels come in a new section, which we call the workflow. So on the left-hand side, you'll see it's very similar. You have the inputs, the outputs, and the script section. And on the right-hand side, you've got this ability to define actual complete workflows, and which in themselves can have their own inputs and outputs. And it just allows a little bit more modularity of the language as well. Going back on the concept of data flow, which is consistent across all of this. So you can think about the idea of that these processes, I said, are alive. They're kind of sitting there waiting for the input. And as soon as they receive that input, it's executed. And the thing which links these processes together is these channels. And the channels are these asynchronous first in, first out queues. And they are the things that are kind of driving the execution of the processes. You can think of the processes as sort of waiting there. As they're received, they create a task. And this task in itself is it's a kind of instance of the process. So just to put like the kind of wording here correctly, you can see that we have a channel, and we've described this channel as having 3 elements. In this case, they could be files, they could be values, they could be whatever, but in this case, we've got 3 of them. Because we have 3, in this case, 3 elements in this channel, we have a process definition which will result in 3 tasks being executed. In this case, 1 for every file itself. And they're actually, those tasks themselves are happening purely in parallel, even at the CPU level or at the execution level as well. What does it look like in practice? Well, imagine that we had a channel here which was containing a single sample.fastq. And then we wanted to define, for example, the fastq process, the fastqc process here. So the fastqc process would just take this single sample and run through once, and we would get 1 task of fastqc because we have one sample. If we simply change the channel definition and we said, actually, I want all my FastQ files or all my FastQ files run through, then for every one of those FastQ files, this would run through this as well. And this would be kind of the result of that parallelization. You can visualize this in a slightly different way here, where I've got the individual channels going through, the channel going through with the individual data files and resulting in that as well. Okay, a little bit some comparisons with the syntax of Nextflow versus CWL. We've got this kind of obvious comparison here between one as being a specification in CWL, whereas something like Nextflow is much more around both the language and the runtime. So those two things are combined. Obviously, a big difference with being a DSL in that it's a domain-specific language, so it's not sort of strictly, you can sort of use what's outside the specification as there. Nextflow seems to be quite fluent in the sense that it's quite easy to read. It should be quite clear what's happening most of the time when you're kind of reading it from the definition of those processes as well. And this concept, we have this kind of single implementation, which means that the language itself is very quickly linked to the runtime. You don't have multiple implementations of it. You don't have variances, which can result in much sort of quicker iterations and quicker development times. Nextflow is definitely much more similar to something like SnakeMake. In this case, they both really kind of started off as command line tools, obviously both very popular in the area. The major difference here between Nextflow and SnakeMake is this concept of a push model versus a pull model. So with SnakeMake, it's actually when they start the pipeline executing, you have to wait for that whole graph to be generated. Once the graph is generated, essentially going from the bottom to the top, only then the execution can start. Whereas in Nextflow, you've got this concept where the pipeline is essentially driving from the top, which can be much quicker. I'm not sure how completely up to date all of these things are, but certainly Nextflow has much better support for the container runtimes for a long time now, and that really means through all the different container runtimes. I think Nextflow supports 5 or so of those, as well as for cluster and cloud, and particularly this sort of cloud execution has been a big driver for Nextflow's adoption as well. Okay, so that was a little bit on the syntax itself. What if we consider some of the deployment scenarios? So we're going to be running today in the next few days, mostly like a local execution. And this is typically used for when you're developing pipelines or maybe just running on a single virtual machine, maybe your single laptop. And it really kind of looks pretty basic. You've got Nextflow run, you essentially run the Nextflow pipeline. You can do this with or without containers, but we'll see later on, it's pretty much recommended to use containers everywhere. And the concept here is that each Nextflow task becomes a process which kind of runs on your operating system there with this local storage there. And it's kind of a fairly sort of standard way for development, as well as testing and the like. What becomes more popular is particularly when you have sort of larger data sets or you're running in a university environment, is this concept of a centralized cluster execution. Here, Nextflow takes each task, so like each of those tasks essentially gets wrapped in a Slurm wrapper, for example, or as a Slurm class and submitted to the cluster of your choosing or the queue of your choosing with the resources that you define as well. And here, it's important that the intermediate files, the files which generate or the input files are typically accessed via the shared file system here as well. What's become really popular in the last few years, there was these managed services in the cloud. So this is things like AWS Batch, but also Google Batch and Azure Batch now. And in each of the cases, it's very similar. Nextflow is submitting the task to the Batch API, for example. And from there, the individual virtual machines are kind of spinning up those resources on demand. And then the tasks are being placed on there. When there's no more tasks in the queue, the virtual machines shut down. And this can be very cost effective when you have, say, a large sequencing run that you need to analyze, or maybe resources that you don't have available to you on your local cluster, or when you're just not really running that much. It becomes very cost effective to run these things. And with the use of spot instances and some of the optimization that we're doing, this becomes a very effective way to run your analysis as well. Looking more in the future, there's obviously a move towards having more cloud native-like execution. And this is really where we believe Kubernetes is going to play a big part. Nextflow has support for Kubernetes. There's obviously quite a few large industrial use cases where Nextflow has been used in this setting. And we see the kind of more evolution of this as it expands. There's obviously a little bit more setup here. You have to manage the Kubernetes cluster yourself, which is not something I recommend for people if they're just starting out. Okay, a little bit on the portability now. So what does that look like in practice? I mentioned the different computer environments. How does it look if you want to go run a pipeline like that across those environments? So if you can imagine that we start with our Nextflow script here, if I was to say Nextflow run and just run that locally, it would run that script locally on my machine, and obviously the pipeline would run there. We've got this concept of a Nextflow configuration, which is how you can define the execution itself. So if I, for example, had a configuration here in my file, I'm going to say, I'm going to define, in this case, an executor, a queue, some memory, 8 GB here, some CPUs and some container image. Now, each of those tasks is going to be submitted to, for example, my Slurm cluster with this queue, and it's going to run each of those tasks on that as well. And you'll notice, importantly, the script section remains exactly the same. So it's the same workflow, it's just defined. And then again, this is this real clear separation between those two things. The next step, if I wish to take the same pipeline and run it on AWS Batch, for example, I can simply switch out the executor here. There's the concept, there's abstractions which exist for queue and memory, CPU, etc., all remain the same, and that really enables that portability across that without having to change the actual script itself too much. So just to stress the point, really decoupling those things is important, and something that we hopefully can stress a little bit over the next few days of this workshop. A quick sentence on containerization, or a couple of sentences. So containerization is really key to a lot of the stuff that we're going to see over the next days. It really drives a lot of the portability as well as the reproducibility of these pipelines. So Docker came out in around 2014, and it was really just kind of a few months after we'd started the Nextflow project. And that really allowed us to kind of sort of fit very well with the model which we were developing. Containers have been used for long-running web services for a long time now. We sort of took the concept and sort of wanted to apply it to how we could run data pipelines in this way. If you compare these to virtual machines, you've obviously got a lot lighter, so a lot sort of smaller in terms of moving them around. They can start up a lot quicker, so you don't have this long sort of this problem of the cold start problem, where you're waiting for your virtual machine, even if your task is just going to run for a few seconds. And you've got all of this tooling which exists with Docker, the idea that we can build containers, we've got registries, we've got kind of really nice ways that we can manage all of that software, and that becomes really useful for us when we're trying to build, let's say, 60 or 70 different containers for all our pipelines as well. If we think about the containerization support for Nextflow, well, when Nextflow is submitting in a pipeline, you can think of it as each of those tasks becomes a job, and then that job is submitted to a cluster, let's say. Well, with containerization, each job just becomes a container job. So instead of being a job like BWA mem, it turns into Docker run BWA mem or something similar. And that kind of really enables as well that kind of whole portability across different systems. You'll see Docker being used. You'll also support for Singularity, mostly used in shared environments, things like Podman. And we start to see like a more adoption as well of other technologies, all kind of built around similar standards. So there's a lot of interoperability between those containers as well. And just thinking on when to use containers, I definitely recommend sort of doing this always. Once you get the hang of this can provide so many benefits, really sort of helping yourself, your future self as well, if it comes to reanalyzing things or coming back to a project after some months, or even just how you can, with the containers, you can really build on them now so you can continue to evolve your pipelines using all of that as well. Okay, a few other kind of things on the community. So Nextflow's been growing pretty rapidly the last couple of years. It's a little bit out of date now, but we have around 12,000 people who read documentation every month. And a lot of that growth is really coming from sort of the community of developing pipelines. This is just really highlighting sort of the Nextflow runtime itself, but obviously the NF core communities and people who are developing the pipelines is even sort of larger than this. Again, if we think about some kind of additional tooling that we've got available to us, so if you want to run Nextflow, you've got some syntax highlighters. We're going to use one of these, and I'll show you in a moment how you can set that up as well for writing sort of practical stuff. And obviously NF Core, there's going to be a whole section on NF Core later on, but you can think of it as essentially a way that you've got these collections of Nextflow pipelines which are available to you, but also a whole bunch of really good tooling and best practices for how you can think about setting up your own pipelines or how you can contribute to these ones following those practices as well. So with that, I'm going to stop here, at least on the introduction section. And we can jump over into the main section itself. You can find this over at sakera.io/training or training.sakera.io. It's all the same. I will type this in the chat now. If you type in probably Nextflow training Sakera, you'll find this as well. It should all be in the same place there. I'm going to jump back over to here to walk you through this as well. I believe you can find all of that information there as well. So the main training material that we have is available here at training.sakera.io. Here you'll find this is going to be here forever, so no worries about having to copy this or anything. This is always available. And the main thing that we're going to be using is a Git pod environment, which if you follow 1.2 there, which allows you to have all of the material, all of this downloaded in there. So you can come back to it at a later date or jump in there anytime. If you do want to install Nextflow locally, like on your own machine, and maybe if you want to do this in your cluster later on, or when you want to develop things for yourself, if you go down to the section of 1.1, you can see the main requirements for Nextflow. And the top two ones here are the requirements for Nextflow itself. So you need Bash, as well as Java. Obviously, if you have a Linux machine or a Mac OS or Windows subsystem for Linux, it's typically enough to install this. But if you have any issues, go over to the Nextflow training or always come into the Slack channels for that. For this workshop itself, we're also going to be using Git and Docker. And those two things are obviously kind of core things that are useful. And then if there's a little bit of material in here for using AWS or Singularity, etc., which is kind of more optional and towards the end of that. But for most use cases and for most of the time of all of this workshop, we're going to be using Gitpod. And as I mentioned before, Gitpod it's an environment that you can spin up. And the nice thing about it is it allows you to spin up any kind of GitHub repository essentially inside of a container. So I'll show you what this one looks like. We're basically using this container as this repository for all of the training. So this is public. If you want to contribute to this, feel free. If you want to make suggestions, it's always available. You can go into here and you can see that there is a .gitpod.yaml if you're interested in this thing. Lots of questions about this. And this basically describes how that Gitpod training environment is built. So you can see here that we are installing Nextflow inside of this. We are adding in for example, some extensions here. So we've got the extension for Nextflow, which is just a syntax highlighter, and a few other things for running that. For our purposes, though, we're going to simply click this link here. And when you click this link, it should open you up with a Gitpod environment here. So you can do this. It'll take you 30 seconds or so. And then once you open up, you should be inside of this environment here, where on the left-hand side, you've got some kind of like a file browser here. So I've got basically everything pulled from that repo. And then I've got some space in here where I've got some text editor if I wish, as well as a terminal down here. I'm going to make this I'm going to zoom in a little bit, so hopefully you can see my text a little bit better. And hopefully you can see all that. And then I'm just going to close these windows so you can see everything that I'm doing. I'll just give you 30 seconds or so to get into there. And in the meantime, I will just confirm that I've got Nextflow working by writing Nextflow info. And it's going to show me the version and everything there. And we are good to go. So the first thing that we're going to do, and it may take a few seconds for that to go, I'm not going to start completely, it's just we're going to look into the kind of basics of Nextflow. So there's the material inside of here, which kind of goes over a lot of the stuff that we covered. So the basic concepts, etc., around processes, around channels. But a lot of this stuff is best seen in an example. And the first example that we're going to do is your first script here. And the purpose of this script is, it may seem a little bit trivial, but it actually covers a lot of the different aspects of Nextflow. So there is the concept of parameters, essentially of input to our pipeline. We're going to look at how we can create a channel from that. So kind of the first look at how we can look at those data flow objects. We're going to define two processes. The first one is going to take an input and create some files. In our case, multiple files, which will be essentially treated in parallel for the second process. That second process will treat those files in parallel, And then finally, we'll bring that all together and we'll get a result out of that. And saying so, all of that will happen with software which is available to any operating system or to any sort of bash environment. So we're not going to use any special tools. We're just going to be using things like print, cat, splits, etc. Also tools which should be available sort of anywhere you run. It's obviously including our environment as well. So as I mentioned before, this pipeline itself is very basic. We're basically taking a string as an input, in this case, hello world. We are going to print it to the screen and then split it. And this split process, the split tool, I should say, is just a Unix tool, and it simply takes that string and turns it into a file. So it's going to split it on 6 characters. So in our case, we're going to have hello as the first file and world as the second file. And then the next process down from that is going to take that output of the previous step and use it as input where it's going to cat it. So this is just essentially printing that file that exists, or the contents of that file. And then this is just simply changing from lowercase to uppercase. So in the end, we are taking the input file, we are splitting, sorry, input string, I should say, splitting it into files and then converting it to uppercase. Let's go through that in practice, and just to see exactly what I mean. I'm going to do that without using Nextflow at all, just to show you sort of what's going on here so that there's no confusion. So I'm going to go clear here. The first step I'm going to be doing is just going to say print f, exactly like we have in the first process. I'm then going to take the string, so allow my text there. I'm going to pipe that into the task, which is, sorry, to the split tool. And this chunk is just a prefix. It's just saying I'm going to create files that are prefixed with this. You could put whatever you want there. But in our case, we're going to do this. I'm going to say ls on chunk. And now I'm just going to say, show me all the chunk files. So this sort of one-liner created these 2 files. So if I say cat on chunk AA, you'll see I've got hello and cat on chunk AB world. I know it seems pretty trivial, but you can imagine this as like doing some process that creates some files, and those files you're going to process downstream. And what are we going to do downstream from there? Well, we can think about our files that we've just got, chunk AA and chunk AB. We want to take those and we want to do a cat on them, so chunk AA. And this is a step which will be happening in parallel in a moment. And then I'm simply transforming them to uppercase. So I'm taking them the lowercase to uppercase. So I'm going from lowercase hello to uppercase hello, and then in parallel, the same thing to world as well. Okay, let's just go through the script now before we run this and just see some of the Nextflow specific aspects to this. So the first line, we've got the shebang, and this is something you'll see common at the start of the Nextflow pipeline. It's not necessary to add in here, but it's always good practice for doing so. You've got the greetings parameter. And parameters are special in Nextflow. They are defined with this param scope here. And they're special in the sense that they can be defined in many places. You can define it in the script here. You can put it in the config. You can define it from the command line. You've got a params file, which you can edit in. And the whole purpose of that is that there's maybe many different ways that you wish to change some parameters as part of your Nextflow pipeline when you run the pipeline. We often will have a default parameter as part of the actual workflow script, like the .nf file here, that just sort of runs through the pipeline successfully. Now, the line number 4 here is our first definition of a channel. And here you can see we're creating a channel called greetings channel. So this is an assignment because we're saying greetings channel equals. And then this channel.of is a channel factory. So this is the first kind of look at what we call a channel factory where we're creating those channels. And this channel is very simple. It contains a single element called hello, so which is a string of hello world. So this, you can just think of this hello world gets placed inside here. Now, going through the processes, you can see that we've got a process called split letters, which takes a single input. It then runs this print.f on that input, which is just a value. So it's not a file here. It's just we can tell this from this val here. It's going to pipe it, create our 2 output channels, sorry, our 2 output files, chunk underscore. And the key thing here is that the output of this process is going to capture anything which matches this. So anything which matches chunk underscore star And that's basically, in our case, we know it's going to be chunk AA and chunk AB. Then the next step here is that the process convert to upper, which takes a path. And Nextflow, a path is essentially the same as a file. It's a file object. And Nextflow doesn't make a distinction between actual files and paths in this case. So you'll see path is what we call the qualifier on that input. So we've got path Y. And then for this task itself, it's going to do a cat of that file, and then basically take that and convert the contents of that file to uppercase. And then this is a bit of an interesting qualifier here. Instead of putting it into a value, or instead of putting it into a path, for example, here it's just going to take the standard output. So it's going to take the output of whatever is produced from this task and capture it into here. Now, this is the definition so far of the parameters, of the processes. Finally, we bring all of that together in the workflow, and the workflow is where this is all executed. And we can see that we're defining a new channel called the letters channel, which is taking split letters and is taking the input with greetings channel. So this here letters channel is simply this, line number 8, because this is the letters channel here. It's like an assignment. So it's saying take the output of split letters, and we give it the name letters channel. And then we want to pass in the letters channel into convert to upper. So the letters channel goes inside the convert to upper, which gives us this results channel, which we're viewing. A lot of information in that. We've really pretty much covered everything. So if you captured all that, good effort on that one. But what we're going to do now is kind of go through this a little bit more in practice and see what happens when we start running this. And you can do this as well. So you should be able to say Nextflow run. And then I'm going to run hello. And if you look inside of that directory there, you should see that we've got a file called hello.nf. So I'm just going to run through that. And if you look at NF training here, and if you double click hello.nf, you'll see that file here. So this is just, if you're looking for that, that's inside NF training. I'm going to close this to make this a little bit more legible. So here you can see that this is run through. And the first information that you get is the version of Nextflow that we're running. You can see that we're launching this hello.nf, which is a local script here. You can see that we've got 3 tasks which were executed, this local 3. The first task, which is actually the first process, split letters, is just run once. So the split letters process has produced 1 task. The convert to upper process has created 2 tasks, and we can see that from this 2 of 2. And then the resulting output, the result of all of this is hello world printed to the screen in uppercase. Let's see what happens if we try run that again. So now I'm keeping everything the same. I just pressed up and said Nextflow run hello.nf. And notice how something a little bit different here has happened. Notice how instead of being hello world above, I've got world hello. And when you do this, you'll get essentially random results as well. And the reason for that is that these 2 tasks, which are running through convert to upper, are running purely in parallel at the CPU level, which means you've got no essential way to know which one of them will run first here. And you can see here, this is basically called alternating here. This is kind of very powerful when you imagine this being run across not 2 files, but across thousands of files, where you get this full parallelization of that, and each of those tasks maybe not running on this CPU, but being sent out to a distributed compute infrastructure as well. Okay, so that's a kind of a brief kind of look at that pipeline and how you can execute the pipeline. What about some other information that we see there, or other information that could be useful? Well, in this case here, you'll see that I've got the convert to upper, and convert to upper is saying 1 of 1, but it's actually, sorry, saying 2 of 2. What's actually taking place there, just to be clear, I can show you here, is that I'm just going to take this log here, I'm going to say ANSI log is false. This is just purely for kind of teaching here. But when I do this, you'll see each of the individual tasks written out one by one. Now, when you have hundreds of tasks, it's not very useful because it's very difficult to keep track of. But in this case here, you can see that actually they have split letters which runs once, and then convert to upper the first task and convert to upper the second task. And the other thing that's important here is these hash numbers. So in this case here, you can see that the first task has got 09/CD2. The second task here is 97, etc., 18. And what that number is what we call the task hash. And the task hash becomes very important when we think about resumability and sort of modifying the pipeline and being able to do that. I mentioned that each Nextflow task lives in its own work directory. It's essentially an independent task. And that hash is the actual location of where that task is run. The other kind of nice thing here is that that hash is made up, it's essentially composed of all of the information of the task. So, for example, it's composed of the input files, of the script section, of the container, and any changes to any of those things will change this hash. So the working directory in itself kind of ties together all of these things. And this becomes important when we go to do a resume of the pipeline. So I mentioned I've run through this pipeline. I'm kind of okay with it. I'm happy with it. But then I realized that I've made a mistake or I wish to change something. In my case here, I actually thought that instead of doing this cat here, I wanted to reverse the files. I'm going to save that now. And notice how I'm going to keep everything else the same. And when I run this, I'm just going to say -resume. So -resume. It's just a single hyphen here. When I let this run through here, you'll see that when it launches the first process here, the split letters, is saying 1 of 1, but then it says cached. Whereas the second process, convert to upper, both of those have run fresh from the beginning. And you can see why that is because we've changed now the convert to upper itself. And that has resulted in essentially the hash changing, and therefore it invalidates the cache and it launches those itself. What if I was to do this again? I was to run through Nextflow run hello resume. Whenever I'm using resume, it's essentially going to look up that working directory, see what's available there, and cache those files. So here you can see that the section here, convert to upper, you can see that's cached. And notice this 09CD stays exactly the same. So it's essentially the task has not had to be rerun. And that's being able to do that as well. There are some more sections that we'll see later on this. It's something that you can go a lot deeper into, and there's some blog posts as well on exactly what makes that up and the processes which was happening behind the scenes. Nextflow resume, though, very powerful for when you've got very large analysis, maybe that runs for days, etc. You don't want to have to resume that. But also, you can even do that across pipelines, or you can have colleagues where you've got the same working directory. So if they've run that task before with everything the same, you don't have to run it yourself as well. Okay, let's talk about now a little bit on the pipeline parameters. So here is our first pipeline parameter we defined, which was greeting. And you could think about how you're going to say, like, run this pipeline with some new data, some new input data. Well, one way to do it would be to go into the script itself, modify this here, make some, say, changes, etc., for running that. But that would be a kind of maybe not the most efficient way to do it, especially if our code was in GitHub, or maybe something we don't want to change. And if to change a parameter from Nextflow, we have this option here to be able to say dash the parameter name. So this double hyphen here. So instead of single hyphen for resume we saw, these are for Nextflow options. If we use 2 of them, we can specify the parameter name. So in this case, I'm going to say the parameter name, and then I'm going to put in here, instead of saying hello world, I'm going to say bonjour le monde, and run through this. And one thing you'll notice is that instead of now, if you remember what the first process is doing, it's splitting on 6 characters. But instead of now, because of the way this is set up, instead of having to have only 2 files which are generated, chunk AA and chunk AB, now we've got 3 files which are generated. And again, all those there are run in parallel as well. So they all kind of run through there. And you can see that we get 3 tasks of that convert to upper. What happens if I was to do this and I said, 1,000 files or 100 files, etc. Same way, Nextflow will split up each of those and run them in parallel as well. So you can see here that we end up with 7 of those tasks being generated. And this is, I'm just showing you here a string, but the principles are exactly the same as well for that. Okay. let's just consider the next step then there as well. I'm just going to revert that to show from before. So I'm just going to go back and change my settings there. So I change my second process so that we're all the same, and run through that there as well. There's a final thing which I didn't mention so far, which is this flatten. And what we can think of is to consider what's happening with the flatten. What I'm going to do is I'm just going to copy this section out first and just have a look at what the letters channel actually is. So if we take what we can do here is anytime if you want to view what the letters channel is, you could say, or any channel is, you can do view on this. And this will print the contents of that to the screen. So by running through here, the letters channel in this case is what we would say it's made up of 3 files. So in this case, three files: chunk AA, chunk AB, and chunk AC. But one thing that's happening here is all of those 3 files are the same element. So anything downstream of that would essentially be only run once. So you can imagine here, you look at this, how there's 3 of those files, and the square brackets is the kind of the giveaway there. They are all in the same element. If I was to put flatten on here then, and view that, now when I launch, everything exactly the same. You'll notice that it runs through, but each of the files which is being generated is on a new line. So flatten is the first example of what we call an operator. And operators allow you to manipulate the contents or modify the contents of a channel or multiple channels so that you essentially can get the output that you want. And it's really the channels that, and the contents of those channels which drive the execution, which is why this becomes so important. And let's illustrate that. Let's imagine that, see if you can guess. I'm going to do everything exactly the same as before, but I'm just going to remove flatten here. See if you can guess what would happen here. So now this letters channel, I'm passing it a single element and not 3 elements. So that instead of the convert to upper running 3 times, it actually only runs once. So it's this modification, it's this changing here of the channel itself, which drives the execution different. And we're going to see this a lot more. We're going to see it when we define channels, when we create those channels, as well as how we can modify them. There's sort of 50 or so different operators that you can use to pull all this together. And it's really one of the kind of powerful parts to Nextflow as well. There's a little bit more of a description in the section there if you want to look into that into the 2.4. So below that you'll see that there's a kind of a view of what that looks like as well. But with that, I'm gonna stop the section here because we do have a lot to cover after this as well. So we're gonna take a 10-minute break or so now, and then when we come back, we're going to jump into the section here on basically creating a real pipeline now. We're going to create a simple RNA-Seq pipeline. It's made up of 4 different steps. Here, we're going to start using some real data. We've got some FastQ files. We've got some FASTA files. And we're just going to run through that with some real software and get going on that. So I'll stop it here. Maybe we can come back in 10 minutes or so at 5 past the hour. Other than that, we can. I'll see you all very shortly, and I'll be passing you over to Abhinav, who will be driving the next session. Thanks very much, folks.
Welcome back, everyone. The small break is over, and let's get moving with the rest of the session. And in this session, what we are going to cover is we are going to build a proof of concept RNA-Seq pipeline, building upon the concepts that Evan has already shared earlier. So this time we will try to dive a bit deeper and then start off from parameters and finish off with a series of pipelines, a series of processes, and complete the pipeline. So for people who are joining just now, I would like to highlight that the details about the event are on NF-Core website. And if you would like to ask any kind of questions, please feel free to join the channel on NF-Core Slack. And if you're not a member of the Slack channel already, then please feel free to join using this link. And our team would circle back on any kind of questions you might have. And yeah, so before we move on, I would quickly like to show the data sets that we have already. And this would be available for anyone who already has a Git pod environment up and running. And we can, if you go to the left-hand side and click on this Explorer option, you will see these folders: ASCII docs, hands-on docs, NF training. So what is relevant for us today is the NF training folder. And within this folder, you will see a folder called data. So in the data folder, we will have a lot of subfolders, but the most relevant one for us today is the data set for chicken genome. So we have a transcriptome file for the chicken genome, and the location of this is a standard FASTA file. So we have from chromosome this until here, and we don't have a lot of data. This is not a full data set for the chicken genome because we want to keep the pipeline and the iteration times very short and fast. Similarly, we have FASTQ files from the gut, FASTQ files from liver, FASTQ files from lung. And these are what you would expect from any kind of FASTQ file. We have the read ID, we have the quality scores, and we have the sequences themselves as well. And that being said, for the rest of the session, we will make our way through a series of scripts, and the relevant section on the training documentation, and the link for the training documentation is already shared on the Slack channel. We will cover section 3. So in this section, I will just make my screen wider. Yeah. So in this section, we will create a proof of concept RNA-Seq pipeline. We will index a transcriptome file. We will do some quality control. We will do quantification on the transcriptome file. And then we will combine the results of quantification as well as quality control into a multi-QC report. So keep in mind, this is not the full-fledged NF-Core RNA-Seq pipeline. So this is not to be confused with the pipeline, which is much more comprehensive in nature. This is just our own proof of concept toy RNA-Seq pipeline. And without further ado, let's get started. So on the left-hand side, again, you will see these scripts are already there on your Git pod environment, right? So let's open script number 1. This script has the content, has basically a bunch of parameters and a print statement. So parameters, as Evan has mentioned earlier, have a special role within a Nextflow pipeline because they allow you to dynamically provide a value which you want to use in your pipeline. So anything which is named or stored in a pipeline using params dot syntax automatically can be overridden, can be used on the Nextflow command line while invoking this script. So if we just invoke this script by default, we will see Nextflow run script 1. It will print the value of reads. And the value of reads basically is this, the location where the FASTQ files have been stored, the one I showed you earlier. But notice one thing. This time, the value, the full path, let me just make it bigger. Yeah, the path is slightly different because in params.reads, we have specified $project_dir, project_dir, and data, ggal, and gut FASTQ files. But however, when we run the pipeline and print the value that is stored in the reads variable, it turns out to be /workspace, nf training public, nf training, then data, ggal, gut. So project_dir is a Nextflow specific mechanism to kind of specify the location or relative locations of your dataset across various scenarios. So right now, the value which is resolved, the resolved value of project_dir is from where I am invoking the script, and my PWD is exactly the path which was appended to the path of data and gut FASTQ files. However, later on we will see that this pattern is especially useful when we are sourcing the pipelines from a Git hosting solution like GitHub, Bitbucket, and we don't have the knowledge of users as pipeline developers. We don't have the knowledge of users' home directory, users' working directory. In that case, project_dir becomes the abstraction layer we can rely upon. So that's that's basically it about the project_dir, and then params.reads. So we can override any of these values, as I mentioned, using command line, Nextflow command line, and anything that has been encapsulated using params scope automatically gains access to the command line. For example, if I want to override multi-QC, and over here I want to say my, oh well, I need to add, well, let's override reads. Otherwise, we need to add other parameters to the script. We say my custom FASTQ dot. And this time, if we run the pipeline, the value of reads would not be the default value mentioned here. It would be the one that I have specified on the command line. So a standard best practice for specifying whenever you write parameters in a pipeline is to specify the default values, right? And then users can, the people who are running the pipeline, they can always customize those values while invoking the pipeline. Now, you might wonder, why don't we use a default variable, for example, like temp or var? So we can use this in the script. However, this var, my variable, this would not gain access to the command line because Nextflow provides a special status to params scope. So if anything you want to expose on the command line, we recommend that you use params dot that variable name. Yeah, so after the first script, and just a quick note about all of these scripts and sections, the first script talks about parameters, but it has a corresponding section on the training documentation. So we have just covered this section. However, with every section, almost every section, we have a couple of exercises. So let's try to go through these exercises for the next minute, and then I will basically move them on, cover them as part of the next script. So just a quick 1 minute break. Also worth highlighting that the answers are available on the documentation itself, but you are highly encouraged to just try and apply these principles that we are learning. The first exercise is basically about adding a new parameter called outDIR, and then giving it a default value. For now, it could be anything. Okay, then the second exercise is about thinking from the user perspective. So when you make the pipelines, you have default values, and some values could be overridden by the user, right? But a best practice is to print out all of the parameters of the pipeline when it is being invoked, so that nothing stays hidden. Because let's say a parameter X was required by fourth process in the pipeline, fourth step in the pipeline, and the fourth step would fail because of the fact that params.x was not specified correctly. So this does not make a good user experience, and that's why this exercise highlights a way you can use to print out all of the possible parameters, whether they are overridden or the default value, at the beginning of the pipeline. So for anyone who has not been able to guess or figure this out, it's not a problem. We provide the answers. And if you move to the next script, the solution is there as well. These scripts build upon each other. And let's move on to script number 2. And close script 1. So in this script, we can see that there is already a parameter called outdir, and its value is results, or rather we should say its default value is results. We can always override it from the command line. But the most interesting part is the usage of log.info, which kind of prints out all of the parameter values that someone might override, or like if the pipeline is using the defaults, the default value would be printed. If this value has been overridden, then the updated value would be printed. So let's run this through. Well, we can copy this. If you want to experiment with the previous script, you can just copy these 2 sections and add them here, and then run the pipeline again. Yeah, so you see this banner, and this is probably the reason for anyone who has been running NF core pipelines, that you see that green apple and a list of all of the parameters. So that is a good real world or production usage of this technique. And you see the updated value for reads is showing up, and then the default values for transcriptome and outdir are there. So with this, let's move on to script number 2. And in script number 2, what we are going to focus on is our first building block of this pipeline, of proof of concept pipeline. So one thing I would like to highlight right now is the process block, and it might help you to think of process as a blueprint of all of the tasks that your pipeline will run, right? So a process consists of specific sections, which we call directive in the Nextflow DSL language. So input is a directive, output is a directive, script is a directive. And these are the most common directives that you will see in a process definition, but there are a lot more. So if you open the docs here again, and if you move to section 3.2, you will see the documentation for process directives. And we have around 30 process directives, and they are used in specific cases, depending on whether you want to control the parallel execution of tasks, or you want to run on a cluster with specific options. You want to run in a cloud environment or Docker container. So we have around 30 directives, but the principal ones are input, output, script. So you can think of a process as a blueprint which specifies a contract, right? Now, why do I say contract? Contract is something that any other process, or technically any other channel, any other part of your pipeline which wants to interact with this process has to satisfy that contract. So there are some internal contracts and external contracts. Let's talk about whatever is within the process scope itself. So within the process scope, we see input, and input has the content of input is basically a path and transcriptome. So transcriptome, like what do we gather from this statement? It means that the input of index process is supposed to be a path type value. Path type value is, of course, something like this, which is a full path that Nextflow can then build upon, right? So the input needs to be a path type value, and it would be called transcriptome. So this value itself, the name of the variable, the prefix is what we call qualifier. The name of the variable is something you can use within the script section. So if I change something here, let's say my transcriptome, then I'm kind of breaking the contract, internal contract, because now this value, the name of the identifier here, is different from what would be staged, right? So we need to make sure that these contracts are satisfied. And then let's focus on the script for a moment, because input, as soon as the process starts, it takes care of the input, runs the script, takes care of the output. So the next logical seq directive we want to discuss is script. And in this script, we want to run the tool called Salmon. This is for doing the indexing of the transcriptome file. And here you see we are technically between these triple quotes, we are mixing the Nextflow DSL, domain specific language, with the shell language. Technically, you can put in any kind of Python script or Ruby script or whatever scripting language you prefer. But by default, it is expected to be a bash script. So when this blueprint receives a specific file, it creates a task specialized for that file, right? So if you go into the task directories that Evan has mentioned earlier, like the process hashes, you go into that, you will not see these variables. What you will see are specific numbers or specific paths, right? So input is a directive which is used by a script. And then when the task is run, the output, in this case, we have mentioned or specified the output to be Salmon index folder. So the output Salmon index has been specified to the index process definition that as soon as script is complete, stage Salmon index, stage it out. So staging something in a process and staging something outside the process. So that's the overall flow within a process. Now, I have not mentioned anything about task.cpus yet, but this is the time. So task is a special value within a process. So this task has a few, you can say, fields, and these fields are pretty much the same as all of the directives you will see here, process directives. And then when a process has been specialized into the process blueprint has been specialized into a task, you can use things specific to the task. For example, CPUs is a directive, and we can specify CPUs within the process. But since we have not specified it here, this value would default to 1 CPU. So by default, any of your process would require 1 CPU to run and would make use of 1 CPU. So we will run this pipeline next and try to understand how all of this works out in practice. The workflow section, the workflow keyword is new to DSL2. And what it helps us do is basically connect the definition, the invocation of a process to another, to a chain of process calls, right? So in this version of Nextflow, the DSL2 version, the definition of a process is different from invocation of a process. So this means that the closest analogy that you can think of for a process, but not a perfect analogy, let me highlight. The closest analogy would be of a function. So you define a function, for example, in a language like Python, add 9, and you can define everything within that function, right? But to call that function, you have a specific syntax. You say add 9, and you provide the argument to that function, right? Say 1. So similarly, for invoking the process index that we have defined earlier, we provide an argument. In this case, the argument is a params, which is transcriptome _ file, and the default value of this is the file path to the transcriptome file. And yeah, so this is how you can invoke a process. Let's try to quickly run this script. Yeah. This time when we run the process, when we run the script, we ran across an error, and the error basically says we have to focus on the command executed. So you can see this was the command executed within the task, and the command error highlights that Salmon tool is not found, and that is true because we have not installed Salmon on our Git pod. To run with Salmon, you'd need to add the argument or the Nextflow command line argument with Docker, and then the Nextflow runtime will make use of the available Docker container which has Salmon installed to run this script. Yeah, so this time the process completed, and again, if we look into the work directory and the process hash and check the command.sh file, the script file, this is the final task definition or the task which Nextflow ran, right? And with this, we are done with second script, and I'll give quick 30 minutes for doing the exercises next. 30 seconds, sorry. Yeah, so it is not very effective or, well, command line friendly if you always have to specify with Docker for all of the pipelines, right? So what we can do is simply add docker.enabled to the nextflow.config file. Docker.enable to Nextflow config file. And now we don't need to specify with Docker at all. And Nextflow would automatically enable the Docker configuration and use Docker to run the script, right? Now, over here, you would notice another option, process.container. And this is how we are telling Nextflow to use this particular container to run the pipeline or run the script, the second script. We will talk more about this in the upcoming session, but for now, we are going to move on to the next script. Feel free to ask any kind of questions you might have on the Slack channel. The team would be very happy to answer any questions. So in the third script, what we are going to do is understand deeper the concept of channels. So we have talked about processes, which are like blueprints of tasks, but they have to follow contracts, right? Contract of input, contract of output, contract of usage of those input and output within this context of script section. However, in this script 3, there is no process. So we are not going to write any process here. What we are going to focus purely on channels. So this part is already familiar to us. We have seen this earlier. Let's focus on this one line, line number 18. Line number 18 basically invokes a channel factory. This is what we call Nextflow, you can say native commands or facilities for creating channels. So channel factory. So there are many other channel factories. So far, we have been using channel off, which Evan mentioned in the context of hello.nf script. But this is another channel factory, which is from file pairs. And this is very relevant to bioinformatics because the FASTQ files, they often have a forward read, reverse read. So, and they differ based on basically the entire name is the same and the orientation is donated by 1 and 2. So if we run this process, script number 3, we will not see anything yet. It will just, Nextflow will just run and exit because of course, we will see log.info, but nothing else of substance. So what we want to do is understand what are the contents of this channel, right? So you can think of, okay, so since we are saving the contents of this channel into a channel called a channel factory into a channel called read pairs ch, we can say view, and this time when we run Nextflow again, we will see a slightly different result. And you see, this is the result, or technically this is the content of read pairs ch. Let me paste this here and highlight a few things quickly. So since this is the content of read pairs ch, or you can also expand and say something like, since this is what is generated by a channel factory of from file pairs, this is a collection of values. So the first value is the sample name. Since we are currently focused on the gut values, it's the sample name is gut. But then the second value within this collection of values is the path, the full path to the forward read and the reverse read. And this is how channel dot from file pairs outputs. This is the shape of output of from file pairs channel factory. If you go back to the documentation, you will see, yeah, you will see that we have linked to a lot of other channel factories. I can quickly mention here. So we have channel factories on the left-hand side, create, off, from, and so on and so forth. So you can also directly specify a SRA ID, and Nextflow would download the sample and then also give you the results in a specific shape, similar to the one we have just discussed, like SRR and then the path. But with this, we conclude our script number 3 and section 3.3. So next, we are quickly going to discuss about about the exercise. Yeah. So the first exercise of section 3.3 is basically a stylistic comment. So since Nextflow, let's go back to our code, script number 3. Yeah, so instead of assigning the value of the value generated by this channel factory like this, using the equal to assignment, what we can do is basically say set and read pairs channel, and this is semantically the same, but just easier to read perhaps. So you start off by creating the channel and you provide the input, and then you store the results of that channel into a different channel name. And if you run it again with read pair ch view, you would see this same result. Yeah, so the same result again, just a stylistic comment. The next section, the next exercise, sorry, is something which is quite useful when you are not sure whether all of the samples that you have specified exist or not, right? So if you go back to the documentation, you will see documentation of from file pairs. You will see that we have options available for every kind of channel factory, right? In this case, what we want to check is check if exists. So right now, if the file that I specify within the process does not, within the channel, if it does not exist, Nextflow would not fail explicitly, right? But sometimes you have situations where you want Nextflow to fail as soon as the file you are expecting does not exist on the file system, right? So a practical example would be, instead of gut, if I say heart, right? If I run, and with this, I would just need to update check if exists, say true. And if I run this script, it should fail. Yeah, because the expected pattern or expected files are not found within the data folder, right? So this is a pretty useful option, and this highlights that all of the channel factories basically can be customized. Their behavior can be tweaked using the options. So we have options for including hidden files when Nextflow does the globbing, and following links if you have a collection, or if you have collected all of the symbolic links into a single directory and you want to run Nextflow using that directory, you can specify something like follow links. And yeah, I think as soon as you start using Nextflow and playing around more with channels, these options become very handy. With this, I'll move on to the script number 4. And script number 4 basically adds another process. I'm gonna toggle some things here so that we can focus on the main content. So in script number 4, we have added a new process called quantification, right? And I would say the most interesting thing that should stand out is the shape of the input which is expected by this quantification channel, quantification process. So let's go back to the terminology of blueprints and contracts. So the quantification process blueprint requires the input channel to fulfill the contract of this shape, right? So it means the input, whenever quantification is invoked, it needs to have the second parameter which has this shape, not the first parameter, because these are positional arguments. But the second parameter needs to have the shape. So let's jump down quickly and let's see how it translates into the usage we want to do. So we create a channel from file pairs, and then we store the results in a read pairs channel, and then we invoke the process index using one file only. This is not the same file that we have used to create the channel earlier, right? This is a separate file, and then here is the file, here is the channel that we have created earlier. Now, as we discussed previously in the command, I can show here, I can highlight here. So this is the shape which satisfies the input contract of process quantification, right? So that is the reason why we are able to specify this channel as the second argument for quantification. So how do we know the shape of a channel? How do we know that it is the content of the channel are in the same shape as we expect? So we can always rely on ch.view. We can always rely on the view operator, and operator is something I will cover as well. Oh, we don't have Salmon, so this would, yeah, we enabled Docker already. Cool. So this is how we know the contents of a channel again, right? And let me quickly mention about the script section of quantification process. So here, since this part we have already discussed, this would default to 1, but we can also just hard code it to 2 or 4. So if anyone is using the Git pod environment, they should have access to a lot more CPUs than just 4. But the interesting part is here. So you see in this, the content of the channel is like a sample and then a collection. Technically, we call this collection a tuple of 2 file paths, right? So what we are doing here is the first argument for Salmon quant command, we are taking the first value of the reads, and the second value of the reads, we are passing it here. And this basically means it gets translated into, I can say, echo true, or not echo. Let's use what we already have. We can say work, and I say here, it says .sh, and here we can see that this file path and the file name has been replaced. This reads 0, reads 1 have been replaced by what we sent into this process, right? So that's a quick overview of all of the changes in this script. We don't have a lot of exercises next, but I think this script still has an exercise. Yeah. So yeah, there is another thing we can do quickly is to use to extend this analysis to other samples, right? So right now we have limited the analysis to only gut samples, but what if we want to run the analysis on all of the FASTQ files within that directory? And in this case, what we will do is resume, because we don't want to rerun the analysis we have already done. And now we can just say resume, and Nextflow should use the cached results from previous runs. So you see this first process is cached, and then Nextflow ran 2 more processes here because the gut samples were already analyzed. Now the liver and lung samples were analyzed again. So you see the caching mechanism is very handy, and you can start off with a small number of samples to develop your pipeline, and then when you are more comfortable and more like sure about how the pipeline behaves, you can just update the patterns. You don't have to like limit yourself to only 5 samples to begin with. And with this, we conclude script number 4. On script number 5, the most interesting change is, I'm just gonna fold the other processes. The most interesting change is about adding a new process, FastQC. Because in the beginning, while we were talking about the design of this pipeline, we mentioned we will do indexing on transcriptome, we will do quantification of the transcriptome, then we will also do quality control, and then final summary using multi-QC. So we have added another process called FastQ. Notice this time we add another another directive. It's called tag. And in this directive, we are using the value that the process will get from the input, right? So what this would do is that instead of showing just 2 or 1 over here, we are telling Nextflow that, okay, if I tag, if you run FastQC and it has a tag, then enrich this information over here on the command line or other locations as well using this tag. So what this means that if we run script number 5, we will see tags on, I think, even quantification, because we added a tag on quantification as well. Yes. Yeah, so this time you see we have salmon on gut, FastQC on gut. And if we disable ANSI log, so because as was mentioned in previous session, if you enable ANSI log, it basically tries to update the overall pipeline status within this one single line, right? But that's a trade-off. You don't get to see all the tags on all of the processes, right? So what we are going to do is we are going to disable the ANSI log, and we are going to update the pattern here. We want to run it with lung and liver samples as well, and we resume. So this time we can see FastQC was run maybe thrice, yeah. And first time it was run with liver, lung, gut, and same is true for quantification step. And this is how you can make use of tagging. Now we have skimmed over one important, well, very important directive, and that is publish dir. Because as of now, all of the analysis that we have done resides within this work directory, right? And if we do tree, we will see there are directories within this directory. Let's do tree 3. And now we see that we have like the results of this analysis within these directories, right? But it's not very practical to store the results in such nested directory folder. And that is the reason why we have we want to make use of publish dir directive. So if I want to publish the results of quantification into a specific location, I can specify here. I can say my quantification results. I can come here. I can just run the Nextflow command again. I can let's run it with resume, so it doesn't actually spend any time in computing stuff. Just uses the cache. So this time cache was used, and there would be a new folder, my quantification results. Yeah. So all of the results generated within this process are now stored in my quantification results directory. So this is how you don't really need to even run the pipeline again. You can just use the cached results to publish some of the files you might want in a separate directory. If I want to publish FastQC results in a different directory, I can just say my FastQC results. right? Another important thing I would like to highlight quickly. And let's let this one run first. Yeah, so again, no processes were run, everything was cached, but the results for FastQC are also published in my FastQC results. So you see, you don't need to run the pipeline again to save the results in a different location. Yeah, what I wanted to highlight is the use of params.outdir. So since we want to allow users to publish results in a directory of their choice, not our choice, we want to rely on publish dir rather than a specific name. Oh, params outdir. And this time, well, this was the default parameter. So the results are already published and they're published in results folder. So we have all of the results within the results folder. And that's how you can provide customizable published locations. With this, we are going to move on to section or script number 6. This is the 6th script. And over here, we see a lot of familiar things already. We see the log info. We can fold this. We see index process. We see quantification process. We see FastQC process. But this time we have another process for multi-QC. So this is, we are almost moving towards the conclusion of the pipeline, because the goal of the pipeline was to have indexing, quality control of FASTQ files, quantification of FASTA file, and creating multi-QC report. So over here, if you want to add any kind of new tool within your pipeline, you have to create or wrap this tool into a process, right? And then everything we have discussed about publish dir, input, output, script applies within that process itself. But for multi-QC, we have an interesting use case. So we have to scroll down and we will focus on this one line, basically. The rest of the lines we have seen already. So this one line, because multi-QC, we can summarize a wide variety of files, we want to use multi-QC to summarize FastQC results as well as the quantification results. So as we have discussed previously, the only way to pass in results or content within a process is through channel. So we have to create a channel, and let's see the contract of the input contract of multi-QC. It basically says it will accept everything within coming in from the channel. It will accept everything, right? So we have to create a channel which combines the results of multiple runs of FastQC and multiple runs of quantification, quant.ch, and put all of these results together and then push to multi-QC. So this is the acrobatics we need to do with channels. So here, what we can see is that we have 3 main channels here, which are the outputs of individual processes. Like indexing has index_ch, quantification, quant.ch, FastQC, FastQC.ch. And since we want to combine the results of multi-QC, combine the results of quant.ch and FastQC, we have to make use of something called operators. We have already been making use of it. We just didn't highlight earlier. So set is an operator. And then similarly, mix is an operator. So let's untangle this a bit. And over here, we can write something like this. This is perfectly valid Nextflow syntax. We just need to maybe assign the values to multi-QC input ch. So this is the channel name that comes to my mind right now. So since we are going to combine the results of quant.ch, the contents of quant.ch channel with the content of FastQC channel, and then collect them together, because we only want to provide a single value or a single collection of values to multi-QC, we collect them together and assign this to or store this within multi-QC input CH. And then this is how we can, operators are essential if you want to do advanced stuff with channel manipulation. So just like channel have a separate section for in the documentation, the Nextflow documentation, you can find a separate section for operators. And everything that we have discussed, or most of the things that we have not discussed even, they are mentioned here. So you see repeated use of view, you see use of mathematical operators, forking operators, combining operators. We have just made use of mixing operator. And the Nextflow docs is very good because it shows you the behavior of the operator or any content there itself, any construct. So this is how it will combine the results together. And if you run this script and add a view over here, we will see what are the overall results. So let's do with 6. We will see what are the content of the channel which is pushed into multi-QC process. Yeah, so this is the content of the channel. So we have fast QC results, and then we have quantification results. But these are only related to gut. Maybe we want to run this with all other processes or all other samples as well. So we run this, and this time, let's go for cleaner terminal output. Let me make this bigger. Yeah, so this is the result or the content of multi-QC input channel. So multi-QC, if we go into the, if we inspect the multi-QC, we say, yeah, we inspect the multi-QC task directory, we will see symbolic links to all of the results of previous tasks, right? Let's just focus on the normal links. So it has fast QC results as well as quantification results for liver, lung, gut, right? And this is how you can combine the output of various processes together. So basically, it would really help you. At least it helps me to think mostly in terms of channel manipulation. So channels have a shape. So if you want to change the shape of a channel according to the contract of a process, then operators are your friends. So with that, we have concluded the 6th script, and we are quickly going to go to script number 7. 7, yeah. And here, again, there are many familiar things already. We have talked about those. I'll just fold them out. We have fast QC again. We have QC. And this time, the only different thing, or the only thing I would really like to talk about is the workflow.onComplete section. So this block is a special block because it works at the level of workflow. So over here, we define a workflow, which is the interaction of channels and various processes together. But when we run the workflow, Nextflow, of course, specifies, tells us that on the command line, tells us that, okay, this has completed, and that's it. So let me just run this again, just to talk about this. So we are on, I'm running script 6 just to show the behavior right now. And then we will move on to script 7, run script 7. So over here, Nextflow tells us that it has run all of the available, it has processed all of the samples as per the pipeline design, right? But if we want Nextflow to explicitly tell us that, hey, your analysis has completed and you need to focus on Yeah, so sorry. Hey, your analysis has completed, and here are the most relevant results you would want to take a look at. So you can easily run. You can do that with onComplete section. And over here, again, this is our good old friend log info. We are going to use this to dynamically update or tell the user where they need to look. So if the workflow succeeds, we want the user to receive this message, right? And if the workflow fails, this is a ternary operator. If the workflow fails, we want the user, maybe this is better. Yeah. So if the workflow fails, we want to tell this message to the user. Otherwise, we want to tell the user, okay, this is the location where multi-QC report is situated. Please go have a look. Yeah. And this is pretty much it with script number 7. And we have completed. Technically, this is called completion event of a workflow, right? So you can use this event for something like triggering an email for your use cases, right? So if something fails, trigger an email. If the workflow passes, trigger an email to such and such person. So you can customize a lot of things, but just to begin with, I think having an on process or on complete event or event handler would be great. So folks, before we jump on to the next section, let's have a quick 5-minute break, and then we will talk about custom scripts, and then move on to running remote pipelines and Docker mostly. Right? Just a 5-minute break. We'll be right back. So welcome back. Before we get started, I would quickly like to highlight that whatever content that we are covering over here, over in the workshops, we will dig deeper into all of these contents later on into different sections. But we want to just cover the big picture first. And Nextflow can do a lot more. There is a lot more customizability of pipelines of design within Nextflow that could be of interest to you. But if you don't, if this was fast, or if you didn't completely catch everything that we discussed, that's completely okay. That's even expected. But feel free to just go through the training content and also to make use of the Git pod environment to go through these concepts again. And also feel free to ask these questions on the Slack channel. Our team is more than happy to respond. So let's kick off this section quickly, and I'll quickly cover the custom scripts, and then we'll move on to the Docker and Conda containers. So let's talk again in terms of script number 7, and I'll undo all of my changes here. So in script number 7, let's talk about the FastQC process. So you see, this process is a little bit different from other processes because it has multiple lines of code within the script section. And if you see multi-QC, that's basically a single line over here. And the same is true for index and quantification process. But Nextflow natively has no limit on how big should be the content of the script section of script directive. But you can easily imagine that this can become cumbersome if you have a very big script and you don't you want to maintain that and read this within the context of Nextflow DSL itself. So perhaps a better way is to just create a new shell script. Any ad hoc scripting language would do, but let's stick to shell script for now, bash script to be precise, and let's add this within our workspace. So what I will do, I will create a new file, and I will call it text file. Yes, I will add the content here. I copied the content from custom script section within the documentation 3.9. And I am going to save this within bin, and I'll call it fastqc.sh, and I'll save it. So this file now exists in my file system over here within the folder of bin, right? The next thing we need to do is, as you might be used to doing with all shell scripts, we have to provide, we have to make it executable, and we do this by running this command. And now the FastQ script is executable. So this script basically does the same thing we are doing inside the FastQC process, right? But this gives us the benefit that we can now remove all of this and just say fastqc.sh, and the script would work the same. So you can see how Nextflow can give you Nextflow gives you a lot of flexibility in the way you can structure your projects, you can organize your scripts, you can connect various processes together, the behavior after the workflow completes. So there are a lot of extension points or configuration points that you can rely upon. So the FastQC process, notice here, ran again because I changed the content of script. So it broke the fingerprint, or you can say the hash of this process was changed. So that's why this process ran again. And because FastQC ran again, it means multi-QC had to be run again because FastQC, multi-QC depends on the output of FastQC. So FastQC ran again, generated new outputs, and new outputs went into multi-QC, and as an after effect, it has to be run again. So all of these scripts are available locally, right? And this with script number 7, we basically conclude the development of a proof of concept RNA-Seq pipeline. But we have a lot of pipelines available in the community, created by the community. NF-Core is a great example. But many other communities or people have published pipelines in their own GitHub repository, right? So what you can do is you can run a remote project as well. I can run, this could be a full HTTPS link, GitHub link. But if you just specify something like this, Nextflow's default understanding is that this is GitHub. So you can specify a different revision, like you want to only run development branch of a pipeline, or a master branch of a pipeline, or a main branch of a pipeline in your environment. And you can do that by simply relying on this -r command. Yeah. And so Nextflow, whenever you run a remote pipeline, Nextflow pulls it locally, stores it in its cache, and then runs the pipeline. So this pipeline, you can, well, this is the full version of our toy and proof of concept RNA-Seq pipeline, which you can run on many platforms. And I would say this is a good pipeline if you want to experiment, customize things on different platforms. So with this, I'm going to cancel this run because this will work. You can try this in your own environments. But in the interest of time, I would like to move on to the next section, which is dependency management for your pipelines. So as Evan mentioned earlier, dependency management is a big problem when it comes to having reproducible workflows, right? So there are two major solutions for this. First one is managing or installing the packages in a specific environment. And the answer to that, the most popular answer to that is Conda. And then packaging everything up into a you can say shareable package is the answer for that is container. So in this section, we will see how Docker and Conda we can work with both of them individually and combine them effectively to have a reproducible tool set that we use in our pipelines. So in this section, it would be great if we can just rely on Gitpod. And the simplest command we can use to experiment with Docker is again run. So coincidentally, that's the only command we have seen in Nextflow as well so far. But Nextflow has a lot more commands like pull, drop, clone, and yeah. So let's just focus on Docker run command, and we will say Docker run hello world. And what Docker would do, similar to Nextflow actually, is it would check whether hello world container exists locally. If it does not, it will go to Docker Hub, pull the container, and then run it and exit. So this is effectively what Nextflow was doing when I ran a GitHub hosted RNA-Seq pipeline. It pulled it locally, ran it, and exited. So we have already pulled a container, hello world container, but this time let's pull a container which is more wholesome. So it takes a little bit of time pulling these containers. So we already have Debian stretch slim container on our file system. And the next thing we need to do is basically let's check how many images we have locally. Docker images, say Docker images. We have 4 containers over here. We have Salmon, we have RNA-Seq, we have Hello World, we have Debian, and this is the tag. So the next step or next thing we want to do is to understand what is visible inside the container, what is available inside the container, right? So to understand this, technically you can make an analogy that you are logging into a container, right? But in terms of Docker terminology, you can run a container interactively. So we will come here, we will run the container interactively, and as you can see, we are inside the container now. So the prompt has changed. If I do pwd, that is just slash, but outside the container, I was in something like slash workspace slash gitpod, right? So now we are in different or a containerized world of Debian stretch slim container, right? And over here, let's confirm if we have Salmon tool or maybe FastQC tool. We don't really have any of those tools here. So what we want to do is create our own custom container and bundle in the Salmon tool so that we can use it in the pipeline, right? So the way we can create a Docker file is you can think of a recipe of a Docker file. So it starts off with certain base. In our case, the base would be Debian stretch slim, because we already have pulled it. We have confirmed that it exists locally. We have logged into it interactively. So we are pretty sure that this works. But if we want to create our own custom container, and instead of creating this one, what I would do is directly package Salmon into it, right? I will combine a couple of steps here. So this is the Docker file. I'll create the Docker file here. Yeah, and added the instructions here. And then I will add the rest of the instructions here as well. So if you just take a look at this Docker file, it is updating the apt-get cache and then installing two tools called curl and cowsay. Curl is quite useful. I'm not so sure about cowsay, how many people prefer talking cows, but we will add here. Yeah, we will add the instructions to create a container which has Salmon tool built into it. So we can go back to the Docker file over here, and then in the end, we can add run, curl, all of this command here. Yeah, and then build the image locally. So I come and just paste it here. Yeah, I have to move the Docker file into a training. I can create I issued the command, build command for the image, and now it is using the recipe I specified to create the container. This is the recipe again, and it will start off with Debian stretch slim as the foundation for everything it will do next, and then it will update the cache, update the environment path, and then it will download and set up Salmon tool. This is already done. So we have created the container already, and we can even log in. We can run Salmon in the container we can check run it like so. Yeah. So now if we log into the container, we can say run it, and we say my image. We will have access to Salmon inside the world, inside the containerized world, right? If we come out, we no longer have access to Salmon. So it's a tool, we have bundled it into a container. The next thing we will do is, so these are hands-on commands that you can use to mount or to give access to a container to your data, right? So over here, we are going to run the same thing, but we cannot do it because we have the container does not have access to the data because it is on the file system of the host, right? Containers are bundled in a very secure manner so that by default, they don't access file system a lot. So we have to run this command to make sure the container, the Salmon inside our container has access to the file that we want to use. And now it is analyzing that file and it has completed the analysis. So it means instead of just using this tool from our own host environment, we can containerize a tool and then give that tool access to our file system, or technically you can just say access to your data, and then you can run whichever tool you want to run inside that container. So this is a great way to kind of make your entire analysis reproducible. And you can publish your containers to Docker Hub and other platforms. But let's move on to running one of the scripts that we ran previously in the session with our custom container that we just created. So this time, script number 2, I can open up script number 2, which just has one Salmon index process. We wanted to run with our custom container rather than using the pre-built RNA-Seq NF container that the team has provided. So we ran it and it's working as expected. So yeah, the same is true for Singularity. And people who are coming from HPC background, you might be aware of Docker. But basically, Docker requires a daemon to run in the background with root access. That's why it's not very accepted in the HPC community. The HPC community tends to use Singularity or other containers. So Evan has mentioned in the presentation that Nextflow already has support for many kind of container systems since a long time. Charlie Cloud, Podman, so we have a lot of containers already supported by Nextflow. So you can apply the same principles. You can build your own container, bundle your dependencies, and run them within your workflow. It's the same principle. I will quickly jump to the Conda section because this is the second part of the equation. So the way we installed Salmon inside the Docker container was basically, I think I can even open it quickly. Yeah, was using curl, and then we do move from one location to another, basically just setting it up using manual instructions, right? But we have tools like Conda today, and Conda also has wonderful community of BioConda. And what they have done is that they have made available all of these software tools used in bioinformatics within the world of Conda, right? So what we can do is that instead of using manual instructions to build a container, we can combine what Conda provides us and what Docker provides us, and then create our containers using Conda recipes, right? Similar to Docker recipe, we have Conda recipes as well. And we have an example of a Conda recipe here. Conda recipe is a YAML file, and then you specify name, channels, dependencies, and you can use a Docker which already has Conda technically, and then create a Docker container using that environment file. So you have the best of both worlds. You have an automated and verifiable and reproducible way of installing your dependencies, and you have a verifiable, reproducible way of running those dependencies. So we can, so creating a container out of this Conda YAML file. I would leave this as an exercise for the viewers, but we have covered a lot of section today, a lot of content today. The one thing I would like to cover and then call it a day, and then we connect tomorrow again. The one thing I want to highlight is the project of biocontainers. So what the bioconda community has done is that they have, since they already have reproducible recipes for all of the software packages, they automatically build Docker containers for each of those packages. So for FastQC, they are doing something very similar. They're using Conda recipe to create the container, and then they have published these containers to biocontainers project. And then instead of building your own containers, you can just use these pre-built containers, pull them and run them instead of building them all the time. That being said, you can build upon these containers as well. But that is, again, something of an advanced usage. And with this, I would say we can conclude the session for today. I think we are a little bit over time. But thank you again for attending this session. I know we have covered a lot of things, and rest assured we will talk more in depth about each of these concepts. But if you have followed through the entire conversation, the entire content, then I think you should give yourself a pat on the back. This was a lot of content. Again, thank you so much for watching the live stream, and have a wonderful day ahead.